Okay, so now we are at with the paper here, so this way I can write things here and you can see. So I'm really sorry about the shade that's going on the paper here, but that's the best I can do here. Okay, so I reproduced the energy diagram that I showed you in the PowerPoint back here. Okay, so we have octahedral geometry, the geometry with coordination number 7 over here. Let me get closer over here. And then the other one with coordination number 5 over here. And remember, we are looking for the energy of each of the systems in different D configurations, and this way we can determine, okay, the reaction will proceed because it's going to find a lower energy system. So for that, we will calculate the ligand field stabilization energy for each configuration, and this way we can decide uh, if the reaction will proceed or not for each different D configuration. All right, so we are going to start with the most simple one, that's the D1 configuration. So there is just one way to put the electron in the D orbital if we have just one orbital. So I'm going to start with the electron over here. And let's calculate the ligand field stabilization energy for this system over here. So we just have one electron in the dyz orbital, and each electron in this orbital is stabilized by a factor of 4. So I'm going to write here the absolute number, so 4. So let's move now this electron to a coordination number 7. So it's in the dyz orbital, therefore we have to keep in the dyz orbital. So it's going to go over here. Now, guys, take a look. We moved the electron from a -4 stabilization energy state now to a -5.28. So let me write here the absolute value. So that's 5.28. And let's do the same thing for the coordination number 5. Okay, let's move this electron from here to here. So it's in the dyz orbital. So I have to put in the dyz orbital. And what's the value of the ligand field stabilization energy for this system? One electron being stabilized by a factor of 4.57. So let me write here the absolute number, the absolute stabilization energy, 4,557. And now what we do is to compare the ligand field stabilization energy for the initial and the final states. If there is a gain in stabilization, the reaction will proceed. If not, the reaction will never happen. What's happening here? We have a factor of 4 for stabilizing the energy in the initial system. And when we move on to the final systems, there is an increase in the stabilization energy. Therefore, D1 metal complexes, they react and they are called labile, okay? Because there is an stabilization moving on from octahedral to any of the two geometries. All right, so now let's move on to the D2 configuration. So let's add an extra electron in the d orbital, starting here with the coordination number 6, because that's the initial state. So let's put one electron over here. So now, how much is the ligand field stabilization energy? We have 2 electrons being stabilized by a factor of 4. Therefore, the absolute stabilization energy for this system is 8. And again, let's do the same thing. Let's move on this electron from here to here. If the electron is in the dxz orbital, it has to go to the dxz of the other configuration. So it's going to go over here. Now let's calculate the ligand field stabilization energy for the coordination number 7 system. That's going to be 2 electrons being stabilized by a factor of 5.28. And then let's get the calculator over here. 2 times 5.28. So that's a stabilization by a factor of 10.6. Okay, nearly 10.6. And let's do the same thing, moving this electron to this other geometry. Again, it's in the dxz orbital, therefore it has to go to the dxz orbital. Right over here. And then we do the same thing. We calculate the ligand field stabilization energy for the system shown over here. 2 electrons, each one being stabilized by a factor of 4.57. Therefore, the ligand field stabilization energy is going to be 2 times 4.57, and that's an stabilization factor of 9.14. Now we analyze the ligand field stabilization energies for each of the geometries and then decide, is the reaction possible or not? At the beginning, we are stabilizing the system by a factor of 8, and if we move to any of the other 2 possibilities, there is an increase in the stabilization energy. Therefore, the system will move to a more stable system, which means the reaction is favorable. The reaction may happen. Therefore, this system is called labile. Okay? The conclusion is D2 metals form complexes that are labile, because if they move to the intermediate state, they gain in energy, or they get more stable. So it's favorable, thermodynamically speaking. And that's why they are labile. Okay, so now let's move to the next configuration. So let's add up one more electron. So a D3 configuration. So starting here with the octahedral complex, so we have 2. So D3, there is only way to do that, and that's by adding a third electron to this set of orbitals. Ligand field stabilization energy, 3 electrons being stabilized by a factor of 4. Therefore, the stabilization energy in absolute numbers is 12. Okay, so that means a D3 configuration in the octahedral geometry is stabilized by a factor of 12. So now let's see what happens if we move on to the coordination number 7. Attention, the electron is in the dxy orbital, therefore when we move to a coordination number 7, it has to go to the same orbital. So it has to go here. Okay, so let's add up an electron here and see now what happens. Now we have 2 electrons being stabilized by a factor of 528. However, we have 1 electron being destabilized by a factor of 2.22. So what's going to be the ligand field stabilization energy then? Well, we have 2 electrons being stabilized by a factor of 528. So let's put the negative here. And 1 electron being destabilized by a factor of 2.82. Therefore, the ligand field stabilization energy in absolute numbers is going to be 5.28 minus 2.82, which means an stabilization of 2.46. Okay, so stabilization of the system by a factor of 2.46. Oops. So hold on, I missed here. I forgot to multiply by a factor of 2 times 2 minus 2.82. Okay, so that's actually, sorry about that, a stabilization by a factor of 7.74. All right, and let's do the same thing for the coordination number 5. So the third electron went to the dxy orbital. When we move to a coordination number 5, it has to go to the dxy orbital. So it will go right over here. And let's see the ligand field stabilization energy of the whole system. So we have 2 electrons being stabilized by a factor of 5.57 and 1 electron being stabilized by a factor of 0.86. Therefore, the total ligand field stabilization energy is going to be 2 times 4.57 plus 1 times 0.86. All the 3 electrons are stabilized in the system. Therefore, the total ligand field stabilization energy is 10.0. Okay, now let's analyze the ligand field stabilization energy for the octahedral and compare with the intermediates. If the system gets more stable, the reaction will proceed. If not, the reaction will not happen. Look what happens in the D3 configuration. The stabilization of the system initially is 12. If we move on to any of the intermediate states, the system gets less stable. Therefore, reactions will not happen, which means D3 metal complexes do not react. Therefore, they are inert. Okay? See how the ligand field stabilization energy can explain why some configurations are more reactive and some other configurations are not. So I'm going to stop here, and then next week we will cover all the other configurations and then move on to square planar complexes. Thank you very much, and I see you next time.